Okay, inside the sun, you've got the sun burning bright. The up quark from the proton to make more mass. This goes back to Einstein's equation that everybody memorizes, but nobody knows what it's about. E equals mc squared. Okay, the energy, 15 million degrees. Right here. 15 million degree Kelvin. The core of the sun is able to fuse the protons to the point where the up quark receives enough energy to increase its mass. The up quark becoming a down quark. Draw it bigger. You will see these letters the same size in any chart in the world. Draw it bigger. The down is more massive than the up. The charge, electromagnetic charge on the up quark was plus 2/3. The charge on a down quark, minus 1/3. So, conservation of energy, conservation of matter, these go back to Newtonian physics. This is modern high energy particle physics. Conservation rules still follow. Electromagnetic, plus 2/3 to minus 1/3, there has to be a positive charge lost somewhere. A positive 1 is carried away by what's called an anti-electron. This is antimatter in the sun. This is not science fiction. I go to conferences all over the country. Graduate students, PhDs, think antimatter is something only on Star Trek. The sun creates antimatter. The first reaction that has happened. So, a positron, an electron with a positive charge, has to also be emitted. Now this is antimatter to offset the matter that was created with the down quark. So we've got a conservation of matter, we've got a conservation of electromagnetic charge. If there's time, I'll explain to you. Electricity and magnetism are the same thing. They just happen to have these direction vectors that are perpendicular to each other. But for simplistic purposes, conservation of charge, electric magnetic charge, conservation of mass. There's one more quantum quantity called spin. We spin like this, but it's an imaginary force that needs to be accounted for. This is where the particle, if you've heard of neutrinos, it's pretty much confirmed they have mass. These neutrinos are pretty fascinating things. They get the Greek letter mu. And from matter, antimatter, because this is an anti-electron, this is actually a real neutrino. When radioactive decay happens, anti-neutrinos are emitted. The anti-neutrino was first discovered in South Carolina at the Savannah River Nuclear Power Plant. Some guys, Frederick Rains, got the Nobel Prize for this. But a neutrino is emitted in the sun. It's so tiny, the mass is so tiny, there's supposedly, I've heard, as many as 1 trillion going through your eyeball right now from the sun. That's how dense they are. These are from the beginning reactions again. So the first reaction in the sun, if you can get this reaction, any element through plutonium up to the biggest now, which is probably verified anyway, 112 protons, 180 some neutrons, all started at this phase in stars. The sun is doing this right now to make helium. We have to be older than the sun. There's elements, carbon, iron in your blood, carrying your hemoglobin's oxygen and carbon dioxide around. That iron was created in stars before the Earth could even be revolving around the sun. because the sun is still making the first step of neutrons. I was going to have this drawn out for you, but I'll just draw it as you watch here. Proton, proton, neutron, neutron. This is what's known as the alpha particle. Greek letter alpha. Helium. This is what the sun's making. Now the sun at 15 million degrees is not enough in its evolution in the future, as they call it, will become more helium than there is hydrogen. Two heliums do not stick together. Three heliums, two protons, it's got a total mass of 4. This is how the alpha particle is written. I'll go back and show how the sun makes helium-4 instead of helium-3. This is something Hans Bethe proposed. At 100 million degrees, in giant red stars, they look cool on the outside because they're red, but in the core, at 100 million degrees, is able to do something called the triple alpha process. Triple alpha process. Two heliums won't stick together. When 3 heliums come together, this makes the life essential element, carbon. Carbon-12. This is where life is now able to start coming and form. Add another helium, because you got to picture these stars are vibrant, they're alive, they're smashing, they're coming apart, they're combining, they're changing their mind. Carbon-12 plus a helium alpha particle, another bombardment. Now you've got oxygen (16). Another life essential element. Between carbon and oxygen, these are the two. Through other reactions in between here is nitrogen. Okay, these are your most life essential elements. But see, these are your even numbers. Lastly, here through this alpha process, you would come to neon. 12 to 16, this would be neon 20. So a red star at this point, Betelgeuse, is up there fusing heliums to carbon, oxygen, neon. These will all be created in the same environment. Next, the star will have to burn all its helium to these elements, neon, maybe all the way up to magnesium. Then gravity will have to raise the temperature even higher. Perhaps 500 million degrees. You'll start seeing elements like silicon. And silicon burning becomes a term that the astronomers, cosmologists like to use. Stars are burning. Burning is an earthly concept involving oxygen and carbon. These are nuclear fusions that are way higher energies than burning or combustion that we tend to think of. So later, silicon and silicons are pushed together. Carbon-12s pushed together. Calcium's made. These are all stops along the chart of the nuclides to higher elements. I'll leave that up there for a moment to look at. Triple alpha, 3 heliums. 2 heliums will not stick together. They'll fall apart so fast that if another helium doesn't hit it, carbon won't be formed. The element would be called beryllium-8, but it doesn't happen. Now, back to what makes this teaching technique so unique. You'll see this thing called the standard model. I'll write it up here like a classroom lecture here. Standard model. It's simply a table. You should call it the standard table. So as we list our quarks before, as we did, we have the up at plus 2/3 electromagnetic charge. The up is the smallest quark there is. That's why it's so tiny you can barely see it there, right? Now the down quark has a negative charge. We'll draw that a little bit bigger, minus 1/3. Okay? This is the history of the universe in a nutshell. A third grader can learn. This is what they teach in graduate level physics at the university. When we were talking about the Big Bang, the big expansion, at high energies, high temperatures, small volume, the quarks that were around were top and bottom. There were antimatter particles that were created also. There's an anti-top. It's T with a bar. There's an anti-bottom called B bar. Now there's a force carrier involved. It's called a tau particle. It's a Greek letter tau. With that was a tau neutrino. There's an anti-tau and an anti-tau neutrino. These have been discovered now in Chicago, the Fermi lab. As the universe expanded and got cooler, the next row of particles were known as charm, and strange. The force carrier for this second generation is called the muon. It's a negative electromagnetic charge. These were the first particles discovered. Strange, then charm, then the bottom, and then finally the top. Now, for all matter that we know of that constitutes the universe and the earth and life as we know it has cooled to just the right temperature, just the right volume, all the conditions. We have the up quark and the down quark. The electron is the force carrier. An up quark has a positive charge of plus 2/3. Now, when Murray Gell-Mann proposed this at Caltech in the early 60s, fractional charges were unheard of. A more massive down quark has a negative 1/3 electric charge. An electron has a full -1. It was never believed that we could have fractional charge.